Math 1314, Chapter 6, Matrices and Determinants, Section 1, Matrix Solutions to Linear Systems, Video 1, From Systems to Matrices. In the previous chapter, we studied solving systems of equations using a variety of techniques. Primarily, the two techniques that we used were substitution, where we would solve one equation for a variable and substitute it into another equation. And the other technique that we used primarily was addition or combination or elimination, however you want to phrase it, where you would progressively combine equations in an effort to make a variable disappear to eventually reduce it down to a single variable, find its value, substitute, and find the values of the other variables. 1 second, folks. Be right back. Okay, that seems to be a little bit better. I was trying to eliminate the gap between my head and the headphones because the background doesn't project very well there, but oh well, this will have to do. All right, so as I was saying in the previous chapter, we've been solving some systems of equations using a variety of techniques. But one thing about solving a system of equations, and in particular a system of linear equations, and remember, linear simply means that the highest power is 1. So we could have something like x, or we could have something like y, but we couldn't have something like x squared, or we couldn't have something like x times y. Just single letter to the highest power. But one thing about solving a system of linear equations is that the solutions depend pretty much on the coefficients of the variables and the numbers on the right side of the equal signs, and not necessarily the actual letters themselves. As long as we know which numbers go in front of which letters, we really just need to focus on the numbers and not the letters. And so the goal of this video and this series of videos is to approach solving a system of equations by focusing solely on the numbers that are inside of them and their positions, as opposed to the actual letters that they're attached to. And at the end, we can pick up the letters. It's kind of like when we do synthetic division, where we focus on the numbers and the positions, we throw away the letters, and then at the end, we put the letters back in if necessary. So before we do any of this, we need to figure out what I mean by matrix, whose plural is matrices. Again, this word is singular, 1 matrix. This word is plural, 2 or more matrices. But what is a matrix? And no, it's not a movie trilogy with Keanu Reeves, although it kind of is. All a matrix is, mathematically speaking, is a rectangular array of numbers enclosed in brackets. So let's just, and I'm just throwing some numbers up here at random, 2, 7, 4, 3, -1, 0, we'll put 1.5, 11. And again, I'm just making up numbers, 1, 13, 19, and 71. Well, that's a rectangular array of numbers. Notice there are no commas, they're just rows and columns. But to make it a matrix, it should actually be enclosed in a gigantic set of braces. And that's all a matrix is, a rectangular array of numbers enclosed in brackets or braces, if you will. Excuse me. Technically, those are brackets. Braces are these things, which is not what our matrices will be enclosed in. All right, so what does this have to do with systems of equations? Well, suppose a linear system has the following form, and don't let this intimidate you. All this is 3 equations in x, y, and z. If you'll notice, the x, the y, and the z are kind of hiding in there, and they are all lined up as we normally have when we solve a system of equations, especially when you use a technique like elimination. And if you'll just notice, I'm generically representing the coefficients in front of each letter and the constants on the right side of the equal sign. For example, the coefficients in the first equation are just labeled A1, B1, C1. Coefficients in the second equation I've just labeled A2, B2, C2. I just wanted to recycle using A, B, and C as the coefficients of X, Y, and Z. And the easiest way to recycle a variable is to subscript it. In the third equation, our coefficients are A3, B3, and C3. And then on the right side of the equal sign, our constants are just represented by D1, D2, and D3. And if you think about it, when you're solving a system of equations, you're really focused on the things in blue and orange, and not necessarily the things in yellow. The things in yellow just say, yeah, I'm the guy you're solving for, but I'm just going to sit here and wait till the problem's over. So how can we take this system and make a matrix out of it, and more specifically, something called an augmented matrix? Well, all an augmented matrix for a system is, it's a matrix whose columns represent the coefficients of each variable. For example, the first column would be the coefficients of the x's, which we're calling A1, A2, and A3. The second column would represent the coefficients of the y, or whatever your second variable is, B1, B2, B3. The third column would be the coefficients of the z, or whatever your third variable is, so C1, C2, and C3. And the reason this is called an augmented matrix is that we need to separate the coefficients on the left side of the equations from the constants on the right side. And so we're going to draw a vertical bar. It's what I call an augmentation bar, to separate it from the last column, which represents the d's, the constants, D1, D2, and D3. So the only thing that makes this matrix augmented is that we have augmented a fourth column that represents the right side of the equations, whereas the left side of the augmentation bar represents the coefficients of the variables. It is important before you go from a system to a matrix to make note that your variables are lined up, all the x's on top of each other, all the y's on top of each other, all the z's on top of each other. And so that's all you're doing. You're essentially removing the x's, y's, and z's, replacing the equal signs with one vertical bar called an augmentation bar, and putting the whole collection of numbers inside of brackets and calling it an augmented matrix. It is worth noting that this concept can be extended to more equations and more variables. It's not limited to 3 equations with 3 variables. I could have 4 equations with 2 variables, 5 equations with 4 variables, or any combination of numbers of equations and numbers of variables. For this course, we're going to focus primarily on 3 equations with 3 variables, although we could extend the concept pretty straightforward. So let's practice writing an augmented matrix for a system, and then vice versa. In this one, we're going to write the augmented matrix for the following system. 3x plus y plus 2z equals 31. X plus y plus 2z is equal to 19. And x plus 2z is equal to 25. Now, I'm not concerned with solving this system right now. I just want to represent it as an augmented matrix. And to do that, it's real simple. All you have to do is get a matrix going. As far as the number of rows corresponds to the number of equations. Since we have 3 equations, we'll have 3 rows. As far as the columns, you have 1 column per variable plus an additional column for the constants. Since we have 3 variables, x, y, and z, and the constants on the right side of the equal signs, we're going to have 4 columns. Our first column is going to represent the x's, and more specifically, their coefficients. In the first equation, the coefficient of the x is 3. And so our first entry in the matrix will be 3. And then below that, we want the coefficient of the x in the second equation. Now, of course, this x here, I'm going to highlight the x, but it's not what we're going to write. Actually, I'm going to move that over. What we want is the coefficient in front of the x, and since it's not written there, it's an implied 1. And the same thing with the coefficient of this x. And again, that's highlighted the x, but we're really looking at the coefficient in front of it. And again, the implied coefficient is 1. That would be our first column in our matrix. Our second column would be the coefficients of the y's. So let's go find all the y's coefficients. And again, this y doesn't have a coefficient written in front of it, so it's assumed to be a 1, as is this y. So we're going to start off with a couple of 1s in the second column. But if you'll notice, the third equation is missing the y term. So guess what we should do? Well, we have to put a number right here to represent the number of y's in that third equation. And since that third equation is missing its y term, that means it has 0 y terms. So the coefficient of the y is 0. And in general, anytime you're representing a variable that's missing from a system, its coefficient is assumed to be 0, and you treat it as such. The third column is going to be a little bit easier. It's going to be our z's. And all of our z's are present, and they all actually have numbers in front of them, 2, 2, and 2. And I should emphasize that if it's a plus, hold on, folks. If there's a plus, then that belongs with the 2. And if it were a minus, we would put -2. So shame on me for not setting up an example. That was loud. Shame on me for not setting up an example with a negative coefficient. But all the z's are 2's. The augmentation bar kind of represents all of the equal signs. All of these equal signs right here. And then on the right side of the augmentation bar are just our constants, which is 31, 19, and 25. Close off the matrix, and that's all there is to it. We've literally captured the entire system of equations without writing a single letter. And if you're wondering where the x's, y's, and z's, the truth is they're kind of implied by their columns. You don't have to write x, y, and z on top, but that's what each column represents, the coefficients of the x's, y's, and z's, whereas each row represents an equation. Just watch out for missing terms that have to be represented with a 0. And of course, we're going to be going the other way around, where you start with an augmented matrix and you figure out what system it is. Because our plan is going to be this: turn a system into a matrix, do number math to it, and at the end, turn the matrix back into a system that will give us our solution to the system. So we do need to be able to go in both directions, where we have an augmented matrix and write it as a system of equations. So for this example, let's write the system whose augmented matrix is the following. The first column is 1, 2, 4. The second column is -2, 3, 3. Third column is 4, 0, 5. And on the right side of the augmentation bar is 7, -1, and 6. So how do we write the system? Put the letters back in. Now, granted, the letters, the variables don't have to be x, y, and z, but unless you have cause to use something else, you can assume that the variables will be x, y, and z. So what does this first equation represent? Well, the 1 represents 1x, the -2 represents -2y, and the 4 represents +4z. The augmentation bar represents the equal sign, and on the right side of it is 7. I invite you to pause the video and see if you can come up with the equations for the other 2 rows. Just recircling this because it kind of ran into the second row. I invite you to pause the video and write the remaining equations. Watch out for the 0. Hopefully you paused the video and tried it. If not, here we go. In the second row, that goes 2, 3, 0, and then a -1 after the augmentation bar. The 2 at the first column represents 2x. The 3 in the second column represents +3y. But the 0 in the third column represents 0z's. Now, it's not incorrect to put +0z, but it's also kind of silly to write that because you're telling me what the equation is lacking. Well, guess what? This equation is also lacking w's, t's, m's, pretty much every other letter under the sun. So if a letter is missing, and you can tell if a variable is missing, and you can tell because there's a 0 in the coefficients on the left side of the augmentation bar, there's really no need to announce that that variable is missing. You can just literally leave it out. And then that will equal -1. Now, do I have to line up the equal signs? No. Do I? I do, but you don't have to. What's the third row going to be? What is this 4, 3, 5, 6 going to represent? Well, the 4 represents 4x. The 3 represents 3y, more specifically +3y. The 5 represents 5z, more specifically +5z. And then the 6 on the right side of the augmentation bar represents 6 on the right side of the equal sign. So it's not too difficult to go back and forth between a system of equations and its corresponding augmented matrix. You just need to be aware of 2 things. Number 1, make sure all your letters are lined up when you go into the matrix or out of the matrix. And number 2, if any letter is missing, be aware that that is represented by a 0 in the augmented matrix. And when you go back to the system, don't forget that 0 means a missing term. All right, in the next video, we are going to look at how we can use an augmented matrix to try to solve a system of equations, because right now we haven't done anything to the system besides change the way that it looked.